and therefore I would have 2 pi radians around the circle. So 360 degrees is the same as 2 pi radians. And then there was another effort to use something besides 360 degrees, try to make it more metric. And there's also something which I don't think most calculators use anymore, but that's also would be 400 radians. I'm not sure if it's EN or AN. It's neither look right, but my calculator in college had radians on it. All right, so, and don't worry, I haven't forgotten about that yet. So there's this relationship between the radius, the arc length, and the angle. So I know that if I go all the way around the circle, my angle is 2 pi. The arc length is 2 pi times the radius. So let's say do half a circle. What would the angle be? 1, you said 1?
Or just pi?
Yeah, either way. Would be pi. What is the arc length of half a circle? Suppose my angle is 1 radian. What's my arc length? Again, that's 1 radian there. What is the arc length? Denise, you mouthed something, but I didn't quite catch what it was. How did you come upon this arc length? When I just talked about it, what was this length right here?
60.
No. More generic. Not looking for a specific number.
Oh, it's the, is it the theta?
The angle is theta. I'm looking for this length right here, though.
It was the same length of the radius.
Yes, it was the length of the radius. So if this is theta and arc length, I'm going to let be S. If I give you the angle, how do we find the arc length? What's the pattern? Oh, that's just the way I happen to do it. But the pattern going this way. If I give you this number, how would you, is there something common to each of these to get from here to here?
They're only the same number.
Kind of. What's different between them?
The R and the R.
Yeah. So if I take the angle times the R, I get the arc length. So we have this relationship right here, that the arc length is equal to the radius times the angle, if the angle's in radians. So I have a wheel. As it moves, let's say, so I've got, we'll take the one that starts with the tape there. So that's touching the ground. As it rolls, basically it rolled the distance of that much of the arc. So that arc length matched the angle through which it turned, the angular displacement, times the radius. So we have a relationship for something that rolls if it doesn't slip. Excuse me. If it doesn't slip, then that's the distance it travels. So if I just do the change in that distance over, well, the radius doesn't change, but the angle does. So I've got this relationship. And it takes them a certain amount of time. So if I just divide both sides by time, well, what is distance over time?
Speed.
Yes. And changing the angular distance over time?
Omega.
Yes. Or angular speed. So this is a relationship between linear speed and angular speed.
Would that be a vector?
No, we're not dealing with vectors right here. This is the scalar version. So it's a hint, at least, about how we're going to get from V down to omega as we do this. Questions to here before I actually go through the steps? All right. So I've got a pole right here that I'm going to let fall. And I want to figure out what is the kinetic energy of this pole. Before it stopped. So there's my formula, 1/2 mv squared. So let's, there it is. So I want to find the kinetic energy of the pole, 1/2 mv squared. I've got the pole right here. It is going to fall. Mass of the pole, I can stick it on a balance, figure out what the mass is. Not a problem. What speed do I use? Is the speed of the rod the same throughout? Got one nod, yes. Got another nod, yes. Groundswell, I think we're up to 3 people who say yes. We're up to 4 people. What is speed again? You can do better than point.
Distance over time, right?
Yeah, distance over time. All right, so let's take this wheel right here. What you think about, there's a piece of tape on right here. And there's a piece of tape, well, you can just imagine there's something right there. So as this spins around, that piece of tape is back up here. Is the distance that this traveled the same as the distance that this point traveled? We got a no over there. Logan?
Yes.
So that distance is the same as that distance?
Oh, no. It's, the one in the middle is way shorter.
The one in the middle?
And less distance.
Okay. So the farther out you go, the more distance it travels. Will you agree with that?
Yes.
How about the time it takes to go all the way around? The time it took this to go around versus the time it took this to go around?
Is it
Okay, so this is a greater distance, but same amount of time. So which one, so if it travels the same distance in the same, sorry, greater distance in the same time, which is traveling faster? Here? Wait, wait,
The center?
this, you say this is traveling faster? Let's see if the math holds up. So we are in agreement that this is a greater distance, this traveled a greater distance than this did. I'll just make up numbers here. So I got my big wheel, and I got the point here. Let's say that traveled 4 centimeters. Does that seem like good enough?
Yeah.
And this one right here traveled 100 centimeters. And you said they traveled the same amount of time, so the time would be, we'll just go with 4 seconds. So the speed of this one is the distance traveled divided by the time, 1 centimeter per second. And the distance and the speed of this part was 100 centimeters over 4 seconds, 25 centimeters per second. Which one traveled faster?
The outside.
Yeah, the farther you are from the center, the faster you travel. Didn't you play the game, I was about to say as kids or adults, where you hold hands with a long group of people and the person in the middle just sort of turns like this and the person the farthest away tries to keep up? One student called it, I think like Whip the Dragon or something like that. I guess it was a regional thing. So, yes?
Does that same thing have to do with, like, for instance, track? When you're running around a track, you have to, if you're in lane 6 on the outside, you have to run faster than lane 1, right?
Unless they stagger it.
Yeah.
Yeah. Yeah. That's why there's generally a staggered dart, at least the ones I've seen for those.
Mm-hmm.
All right, so they're not traveling the same speed. Matter of fact, the bigger R is, the bigger the speed is, assuming that they all travel around in the same amount of time. Now, there is this gut feeling that some students have that there's something that is the same to all of them. Well, what is the same to everything in here is that they all have the same angular speed. They all go through the same angle in the same amount of time, just that this has to travel a lot faster than this does. So if I have this thing falling, if the bottom is sort of not moving, and it didn't move particularly much there, this isn't traveling very fast, but this is traveling a whole lot faster. So if I'm plugging into 1/2 mv squared, what do I choose for my speed? Because I got a wide variety here. What would be a nice estimate, do you think?
The average.
Okay, so middle. The middle would be the average speed. Is that good for you?
Yeah.
All right, so you can pick the middle. All right, so we're approximating this. This is a crude approximation. 1/2 times the mass of the rod times the speed of the, I'll just put a C for center squared. I'll do CM for center of mass. Now, it's a rough approximation. We can probably get a little bit better if we think about it as 2 objects and we do the center of the 2 objects. So instead of doing this, we look at this is half the mass, and then we do the center of that and the center of this. I'll just call this 1 and 2. So we can get a better approximation if we do 1/2 times mass 1 times the center of mass of 1 squared, the speed plus 1/2 the kinetic energy of the top half. It's more difficult mathematically, but it's a better approximation. What do you think would make a better approximation? In terms of accuracy, not in terms of the amount of work you have to do.
Maybe the top.
Pardon?
The top.
Oh, use the very top? No, that doesn't, that's going to give us an overestimate. All right, spoiler. Let's think about it in terms of 3 pieces. You know, instead of 2, let's break it up into 3 pieces. Call that 1, 2, and 3. And we'll just do the center of mass of each of those. So, better approximation, 1/2 M1 V center of mass 1 squared plus 1/2, that's middle piece, M2 V center of mass 2 squared plus 1/2 M3 times the speed of the center of mass of part 3 squared. And we can keep going. We could break it up into a whole bunch of pieces. The more pieces we break it up into, the more accurate our estimate's going to be. So now we're going to use some shorthand notation because I don't feel like keeping writing this stuff out. So what I'm going to do, this symbol right here, it's a capital sigma is the letter, but this represents sum. I'm going to add 1/2 mv squared and put a little I subscript there, I, to indicate, well, I is going to go from 1 to, in this case here, 3. In that case, it would go to 2. This is how many pieces we break it up into, and this just means I'm going to do 1/2 m1 times v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared, and I keep going until I get to whatever that top number is. So if I'm going to break this up into a whole bunch of pieces, well, I just want to make that piece really big. So let's make that big. Officially, we'll break it up into an infinite number of pieces. But so recognize I got 3 terms here. Do I have anything common to all 3 terms?
That 1/2.
Yeah. So I can factor that out. We flash back to whichever math this is. If I have 4a plus 4b, that's the same as 4 times a plus b. If I distribute, I multiply 4 times what's inside and I get this. If I factor, I do the reverse process. So I'm just going to factor that 1/2 out. So for So I'm going to factor that out. So I get a 1/2 times the sum of what I'm left with, MIVI squared. Doesn't this seem so much easier? Don't worry. It's going to look more complicated, but it actually makes life easier in a moment. All right, so I've got this MVI, so the speed of the different objects is different for every single one of them. For every single piece in there that's a different distance away. But there is something common to all of them in the fact that they all have the same angular speed. If the bottom is at rest, and this falls, they all have the same angular speed. Because they're going to go through the same angle in the same amount of time. So what I'm going to do is erase some of this stuff. And so I'm just going to take the speed of the object and I'm going to put it in terms of r and omega, the distance from the pivot point times the angular speed. So this is equal to 1/2 times the sum of whatever the mass of that tiny little piece is times Ri omega. Right. Now the reason I don't have the subscript next to omega is the same for everything in there. They all have the same angular speed. And just like the 1/2, I can factor it out. And what I'm left with is MIRI squared. Now, I know it's a lot of letters. Let's questions up to here before I connect it back with the stuff that we've already done. Then let's connect. This right here That's the moment of inertia, or rotational inertia. It's the mass equivalent. The larger this value is, the harder it is to get something to, if it's at rest, to start to rotate, or if it's already rotating, to stop it. And so therefore, my 1/2 mv squared morphs into 1/2 I omega squared. Now, this actually is easier, even though you're looking at, potentially you're looking at that I and thinking, what is the moment of inertia for this wheel? Well, you're in luck. Every beginning textbook will have a chart with formulas already figured out. So, if I have a disk, rotating about its center, the moment of inertia is 1/2 mr squared, where the mass, that's m is the mass, r is the radius. If I have a long skinny rod rotating about the end, the moment of inertia is 1/2, nope, sorry, try that again. 1/3 mass times the length squared, where that's the length. If I have a rod rotating about its center, where that's the length, then the moment of inertia is 1/12 mass times length squared. So the formulas have already been done for common shapes. Solid sphere. I'll just put up a common shape. Solid sphere,